Yeah. Good afternoon, everyone. So sorry for the delay. Something urgent came up. So the last class we had discussed regarding types of rocks and Earth's movements, different types of processes, and also regarding continental drift theory. So in the topic of types of rocks, we had discussed regarding what are rocks, characteristics of igneous rocks, types of igneous rocks, examples, the process which results in the formation of these igneous rocks, sedimentary rocks, the processes involved in the formation of sedimentary rocks, okay, examples and types and their properties, then metamorphic rocks, the process, the examples, formation, the overall rock cycle, continuous changes which are happening. Then different types of Earth's movements are classified into endogenetic and exogenetic forces. Endogenetic are those processes which are changing the nature of the landform above the surface, but happening from inside, right? So exogenetic is changing the nature of the land surface, but happening from outside the surface. So exogenetic process involves aggradation and degradation, and in case of aggradation, there is deposition, leveling, degradation, removal, that involves weathering, erosion, and mass movement. And endogenetic process involve diastrophic and sudden process. Okay, so diastrophic process include the tectonic, isostatic, and eustatic, and sudden process includes the volcanism and earthquakes. So diastrophic, tectonic are the building process, isostatic balancing, eustatic global rise or fall in the sea level. So tectonic movements are classified into epirogenic and orogenic. Epirogenic is the broad, large-scale upliftment which causes the formation of elevated landforms. Okay, so high elevated landforms are those which undergoes no subsidence. Okay, so large scale, creating different parts of the land. Orogenic are along the narrow belts, creating mountains. Okay, so these are like specific parts of the earth where we have this orogenic process, and it involves folding and faulting. Folding is the process of compression, causing the surface layers to undergo so changes without undergoing complete disintegration or breakdown. So that is what is folding. So there it undergoes folds. Okay, so the layers undergoes folds. Faults are the cracks which are found on the Earth's surface. Okay, so that is due to tensional forces. Okay, so that is faulting. So and in sometimes also, so it is due to folding. You can see the formation of faults. I discussed the types of faults. Okay, so symmetrical, asymmetrical, overturned, and then recumbent, and then naps, right? So yeah, overfold, then recumbent and naps. Types of fault includes normal fault, reverse fault, and strike slip fault. Normal is dip slip, reverse is thrust fault, strike slip is parallel, basically transform faults. Continental drift theory was proposed by Alfred Wegener to explain the movement of to explain the changes in the nature of climatic conditions across the earth, and these changes are according to his idea, it is due to the movement of the continents. Okay, so there was a single super continent called as Pangaea and single super ocean Thalassa. Okay, Pangaea got separated into Gondwana land, Angara land, and then Angara land was Laurasia. Between them came Tethys Sea. So it started to widen, and then north-south drift developed, which separated North America, South America, and then India and Antarctica and Australia also got separated. All of them started to drift in different direction. Okay, so causing the present movement. That is what his idea is. The forces responsible for drifting as per Alfred Wegener include the pole fleeing force, which is generated due to the difference of gravity and buoyancy. Okay, so and then tidal force is due to the gravity of sun and moon, causing the tidal effect. Okay, so the evidences are very important. The jigsaw fit of the continents having the exact similarity of coastlines across the ocean separated by so thousands of kilometers, and rocks of same age across the oceans, and the structural deposits. Okay, so the same type of mountain formations across the two different parts of the continent, and the same layers of stratigraphy, glacier deposits. Okay, that includes stelites. The fossils includes the Mesosaurus as well as Glossopteris. Okay, so and placer deposits, gold placer deposits such as the gold deposits of Ghana. Okay, so we are having placer deposits over there. Okay, so they're from the mountains of Brazil. so this was a brief recap. Yes, tell me if there's any doubt. So, how's the preparation going on? Fine. So you must be having the other subjects. It's been some time we had geography. So what all other subjects you had in between? Polity. Okay. So polity is done. Okay. So any other subject? On polity? Okay. So let's move ahead. The next topic is seafloor spreading theory. So the main issue is with continental drift theory. Drift theory was so Alfred Wegener had no idea regarding the oceanic floor. Okay, so there was no much of idea regarding the nature of oceanic floor. Okay, so how thick the oceanic floor is, and how dense it is, and what is its nature. So there was just a rough idea. Based on that, he had come to conclusion. Okay, so the continental crust is Sea layer, oceanic crust is Sima layer, and Sea layer floats over Sima layer. This is the rough idea he had. Okay, so the main issue is the information. So it was not accessible. Okay, so it was not very easily. In fact, it is not even now. It is not accessible much. It is very difficult to reach out to the oceans. It's too deep. Okay, you need a very specialized set of equipments, machines to reach out to the ocean bottom. However, during the Second World War, we developed a method to map the oceanic floor. Okay, so to map the oceanic floor from the surface only, that is sonar. Okay, so and few other things like sonar and few other things, like we developed some of the underground submarines. Okay, so submarines which are underwater submarines which are capable of staying there for longer time. Okay, so going to much deeper level like that. And the overall our idea of oceans expanded. Even war is also one of the reason behind that. Okay, so when the World War was happening, particularly during Second World War, specifically they were, so they were submarine warfare was going on. Okay, you must have heard about Germany's U-boats, right? Okay, so they used to so just hide under the water and attack the ships. So both civilian, trade, every kind of ships. To fight, they had to develop the capabilities of underwater, so the navigation. So during that process, they discovered certain features on the oceanic floors. Okay, so till then we were thinking oceanic floors should be completely flat and empty, or kya hi ho sakta hai. During that part, we discovered that there are huge, very elongated, at the same time tall, mountain kind of structures on the oceanic floor. If this was the oceanic floor, okay, so let's say this was the entire land. This is the water area. We used to think that it should be empty. It should be somewhat like this. We got to know that there are certain structures on the oceanic floor. Okay, so what do we call them as? Ridges. So like this. Okay, oceanic ridges. Many of the times they were found along the central part of the ocean, therefore the term mid-oceanic ridges. Okay, so people used to use this as their advantage to hide in between and make a surprise attack. Okay, so they did all of this during the Second World War. One of them was Harry Hess. Based on his observations which he made during the Second World War and also the further research which he did later, and he collected a lot of data. Okay, so and he comes out with a theory that is called as sea floor spreading theory. 1961 में ये लेके आता है. Sea floor spreading theory was proposed by Harry Hess in 1961. Okay. Because when they made the observations, they were totally surprised to see some of the things which they could not understand at that point of time. What is the reason behind this? So first of all, what is the reason behind the formation of these kind of huge mountains on the oceanic floor? Okay, if you see in the Atlantic Ocean, the central part of the Atlantic Ocean has a huge structure extending all the way from north to south in S shape, in the same shape of Atlantic Ocean. It was totally puzzling. And when they started to explore these different parts, they got to know that these regions, okay, so ये जो regions है, they're totally active. Active means they're erupting lava continuously. Magma is coming out. Okay, it erupts lava, which is flowing from these regions. Okay, so we got to know about the presence of these mid-oceanic ridges. And we got to know that these mid-oceanic ridges are totally active in nature, which is continuously erupting lava. Okay, just a volcanoes. But it is not like a single cone type structure. It is a very elongated ridge, elongated mountain kind of structure. We don't call them as mountains because they are underwater. In addition to this, few more observations. They tried to collect the sample of rocks away from this central part of this ridge. Okay, so when they tried to collect the rocks away from the central part of the ridge, they found out that the age of the rocks are continuously decreasing away. At the center, you find the youngest rocks. You move away from the central part of this ridge, you are finding older rocks. जितना दूर जाओगे उतना older होते जा रहे. Okay, they are becoming older. And most importantly, there is an exact symmetry between the nature of the rocks, age of the rocks, and their magnetic properties, everything. There is an exact symmetry from the center. The rocks which are located, let's say, at 50 kilometers away from the ridge and 50 kilometers away from the ridge, they are exactly the same. However, those which are located on the same side, they are different. This is different from this is different from this. Age, properties, their characteristics, everything is different. But here, if you take out the same distance, equidistance rock from the central part of the ridge, both are exactly similar. This was totally puzzling. How is it possible that they're exactly similar? It is very difficult to have the same type of rock structure, everything. They also tried to collect the magnetic field evidences. You know, magnetic field evidences are recorded on the oceanic floor. Okay, so when the magma comes out, it cools and solidifies. During the cooling and solidification, the magnetic minerals that are present in the magma. Okay, magma contains various different types of minerals, right? So some of these minerals get oriented in the direction of Earth's magnetic field. At that point of time, whatever the magnetic field is there, in that direction it gets oriented. And once it is oriented, it is frozen. It is locked. Once the magma is frozen, you cannot change it, right? You cannot change the orientation. During that slow cooling of this magma, at one particular temperature, all these minerals will get oriented in a particular direction. So if you observe the orientation of magnetic field, there is exact symmetry in the rocks which are located at equidistance, having the same magnetic property. Okay, so and this magnetic field slowly, continuously changes. Even in that, there is one more observation. Up to certain distance from the ridge, you will find some type of polarity. Okay, where the north pole is pointed in this direction, south pole is pointed in this direction. After some you will find opposite polarity. Okay, there are certain patches, bands like this. For some it is normal polarity. Then it is reverse polarity, again normal polarity, again reverse polarity. You will find continuous patches. All these observations were totally puzzling at that point of time, which could not have been explained. To support all of this, to explain all of this observation, Harry Hess gives seafloor spreading theory in 1961. So what exactly is seafloor spreading theory? Seafloor spreading theory says that the sea floor, this is the sea floor, the oceanic crust. Is in a state of continuous movement. Entire oceanic floor is in continuous state of movement. Why? Because of the presence of these parts of the oceanic floor, which is called as ridges. What exactly is a ridge? A mid-oceanic ridge is the part of the oceanic crust which is cracked. There is a basically crack in the oceanic floor. There is some gap. Through this gap, the magma rises and comes out. Okay, where there is gap in the oceanic floor, of course, the magma is coming out from the Earth's interior. अंदर से magma ऐसे ऊपर आ रहा है. This rising magma, as it comes out because of low temperature in the surface and coming in contact with the cold water, it freezes. When magma freezes, what happens? It becomes rocks. But this frozen magma gets attached to both the sides of this part. यहाँ पर क्रैक है ना, बीच में क्रैक है, बाहर आके ये थोड़ा सा इस साइड में और थोड़ा सा इस साइड में accumulate होते जाएगा. Some part gets accumulated on this side, other part gets accumulated on other side. And got solidified. It got totally attached with the oceanic crust. As this older magma got solidified and attached with the oceanic crust, new magma rises again. Okay, there is still some gap always left. This newly rising magma will push the older one away. The older rocks got pushed away. Okay, because of this wedging effect, like it will wedge. The rising magma will push this away. The older rocks gets pushed this away. Okay, so because this is also moving like this is also moving like this, a part of it is coming out, it is trying to come out. As it tries to come out, the entire sea floor gets pushed away here. Because here the rocks, as they get pushed away, new rocks are being formed here. The rising magma itself cools down and forms new rocks, and new rocks will push the older ones away. Okay, so after some time, these rocks will come here, yahan par new rocks are formed. After some time, this will come here, and here the new ones are formed. After some time, this will come here, this will come here, this will come here, here new ones are formed. Like this, the entire sea floor will start to move away from the mid-oceanic ridge. On this side, on that side, on both the sides. Okay? This process is called as seafloor spreading. What is responsible for seafloor spreading? The rising magma along the regions which we call it as the oceanic ridges. It is like a crack through which the magma continuously coming out, and this will push the oceanic floor on both the sides. As both the sides gets pushed away, the sea floor spreads. Spreading means moving away. If it is moving away, basically new floor is building up in between. Naya construction ho raha hai. Oceanic floor is not only spreading, it is becoming bigger and bigger then. Then earth will start to become bigger and bigger. Why not? The rate at which they are getting created, in the same rate, they also get destroyed at another place. There are certain regions which are called as trenches. Near to these trenches, this spreading floor will go down. It will undergo subduction. The process through which the part of the oceanic floor gets consumed below. It's called as subduction. Through the process of subduction, it gets consumed and destroyed. So at one part of the oceanic floor, it is getting created. At another part of the oceanic floor, it is getting destroyed. There is a balance here. Now, whatever the observations we made, all of this can be explained using this theory. Why we have this kind of ridges? What do you mean by ridges? Ridges are basically the parts of the oceanic floor where there is this crack from where the magma is coming out. That is why these ridges are active. They are volcanic in nature. As this magma comes out, cools down and solidifies, it gets attached on both the sides. And as these rocks are getting pushed away, the newer rocks are formed at the center. Therefore, older rocks gets pushed away, newer formed at the center. Therefore, the age of this oceanic floor increases away from the ridge. Okay, it's always increasing away from the ridge. And since those rocks which got separated, okay, so during their formation, ऐसे दो जुड़वा बाई जैसे separate हो गया था ना? Okay, तो हमारा हिंदी मूवी में पुराने टाइम के बचपन में separate हो जाते हैं. सेम एग्जैक्टली सेम दिखता है. ये भी ऐसे वहां पर दोबारा मिलेंगे, यहाँ पर कभी नहीं मिलेंगे. Okay, so like this, exactly same age, same structure, same properties, everything. Magnetic field also same orientation में रहेगा ना at that point of time. And they get pushed away, pushed away, pushed away. After some time, magnetic field gets reversed. Now reverse polarity it will start to show. That is why alternative patches of normal and reverse polarity. So all of this can be explained using seafloor spreading theory. Okay? since they continuously get created and continuously get destroyed, okay, so oceanic crust always remain young. One part is getting created, another part is getting destroyed. So बीच में जो होगा वो हमेशा young ही रहेगा ना, मतलब young मतलब तो it is not going to be very old. Older ones are all getting destroyed. That is why continental crust, oceanic crust, major difference is their age also. Oceanic crust, because of their continuous creation and continuous destruction, they are never older. You will never find a oceanic crust older than 150, 170, 180 million years old. Continental crust as old as 4,000, 4,200 million years old. Now, what is this process of subduction? We'll study about that in detail in plate tectonics. ठीक है, तो उसके बारे में हम डिटेल में पढ़ेंगे. Harry Hess will not discuss too detail over there. So this is the idea of sea floor spreading theory. Any doubts here? Now, how this sea floor spreading theory acts as a connecting link between the continental drift and plate tectonics. It is considered to be a crucial link. It is considered to be a very crucial link for continental drift and plate tectonics. The seafloor spreading theory provides information regarding the nature of seafloor. Till now, we used to think that seafloor is static, seafloor is featureless. We got to know that seafloor is filled with large number of features. Seafloor is dynamic in nature. Seafloor is continuously getting generated now, continuously getting destroyed also. उसका पूरा nature ही continuous मतलब change होते रहता है. So now with the help of this, we move towards plate tectonics theory. You have to bring continental drift theory, plate tectonics theory, and one more idea, isostasy. Continental drift theory, seafloor spreading theory, and isostasy. When you bring all these together, you will get plate tectonics. What was this isostasy? Floating buoyancy. The continental crust basically floats over the asthenosphere. The lithosphere basically floats over the asthenosphere. Is it right? Lithosphere is overall lower density, asthenosphere is higher density. And the density of lithosphere is not uniform everywhere. Where the lower density lithosphere is there, overall there is a higher buoyancy force. Where higher density lithosphere is there, lower buoyancy force. ठीक है, so I'll tell you the role of isostasy. इसी के वजह से जो specific type of interactions होते हैं, the plate tectonics theory was proposed by Morgan Mackenzie Parker in 1967. Morgan, Mackenzie and Parker. Mackenzie and Parker worked together, Morgan worked separately. Okay, they are independent. So finally जो idea आए हैं ये दोनों almost same idea था. But still they are not as famous as Alfred Wegener. Why? But everything right now is explained by plate tectonics only, including the continental drift, including the seafloor spreading. सबके लिए. See, when continental drift theory came, there was nothing before that. Just some rough idea. He changes everything. He will bring that revolution. The way we saw the landforms. By the time plate tectonics came, everything was almost established. We had an idea regarding continental movement. We had an idea regarding oceanic floor. Okay, there was Wilson cycle, and there was the description of the nature of these continents and oceans, isostasis theories. Everything was there. They just have to bring different pieces together and fit them. Okay, so you will get the plate tectonics theory. Okay. There, of course, they have done a wonderful job in bringing this together. But it is not something which is revolutionary as it was in the case of continental drift. It tries to explain, it fills the gaps and explain the things. The plate tectonics is dependent upon the idea of plate. What do you mean by plate? Crust is part of plate. This is crust and then this is upper part of upper mantle. What do we call this as? इसका नाम क्या है? Lithosphere. Below the lithosphere there is asthenosphere. ठीक है? Lithosphere is basically like an outer shell covering the earth from all sides. It's outer shell covering the earth from all sides. Each individual part of lithosphere is what is called as plate. पूरा हर साइड से कवर्ड है. उसका एक पार्ट को हम प्लेट बोलेंगे. डोंट इमेजिन प्लेट टू बी कंप्लीटली फ्लैट. कर्वेचर है. बिगर द प्लेट, बिगर द कर्वेचर. Okay, so the dimension is not completely flat. People imagine it to be flat. So basically this one part is a plate. ये एक plate हो सकता है. That includes the upper part as the crust, lower part as the mantle. Upper part of upper mantle particularly. Upper mantle का upper part है. So like this. It may contain oceanic crust or continental crust. दोनों हो सकते हैं. This entire part of the lithosphere is what is called as plate. Like this. This is the oceanic crust, this is the continental crust. Below that there is upper part of upper mantle, and then below that there is asthenosphere. Now this part of the plate, part of the lithosphere, lies over asthenosphere. Asthenosphere is like semi-solid, semi-liquid in nature. Okay, it's like a cushion. What is the nature of plates? Hard and rigid. Okay, totally hard and totally rigid. That is the nature of plates. The idea of plate was provided by, who gave this idea of plate? J.T. Wilson. J. Tuzo Wilson. In the year 1965. So don't get confused with T.J. Wilson. There was another Wilson called as T.J. Wilson. He was also geomorphologist. One is J.T. Wilson, another one is T.J. Wilson. He is the one who gave this idea of plate. Plate is the uppermost layer of the earth, hard and rigid outermost layer. The entire Earth's lithosphere, the outer shell, is divided into different types, different plates. Some of them are larger in size, they are called as major plates. Some of them are smaller in size, they are called as minor plates. They are major plates and minor plates. How many major plates are there on the Earth? Number one, Pacific plate. The largest of all is basically Pacific plate, and this plate has only oceanic crust. There is no continental crust. दोनों हो सकता है. Okay, there is a possibility that both can exist, but in this case there is only oceanic crust. North American plate, South American plate, African plate. Can you see one side there is continental crust, another side oceanic crust? Below that there is upper mantle. Okay, below that there is asthenosphere like this. Fifth one is Eurasian plate, Europe and Asia. Okay, sixth one is Indo-Australian plate, entire Indo-Australian plate. Seventh one is Antarctica plate. Fine. 7 major plates. In between these major plates, there are minor plates. For example, Cocos plate, Nazca plate, Caribbean plate, Arabian plate, Anatolian plate, Philippines plate. तभी ये सारा मिलके एक ऐसे single shell बनेगा ना. There are many smaller plates, they are called as minor plates. The plate tectonics theory believe that these plates are not completely static, being present over asthenosphere. They are in continuous movement. They're capable of continuous movement. They move in different directions. And that results in 3 types of boundaries. Okay, so नीचे वाला छोड़ दो, ऊपर का देखो. When 2 different parts of the plate interact with other plates, and if there is movement away from each other over there, it is called as divergent plate boundary. 2 parts of the plates moving away from each other. Divergent plate boundary. Okay, so plate margin is that part of the plate where it is interacting with the other plate. It's called as plate margin. When 2 plates are moving towards each other, convergent plate boundary, the second type of movement. When 2 plates are sliding past against each other, transform or parallel plate boundary. So basically there are plates. Plates are hard, rigid outer layer of the Earth's interior, which is moving over asthenosphere. It is because of the movement, okay, because of their nature, that different types of boundaries exist. Divergent, convergent, transform. Now what are the differences between continental drift and Plate tectonics now. Continental drift believe that continental crust is moving over oceanic crust. Plate tectonics believes that lithosphere is moving over asthenosphere. It is the plate which is moving over asthenosphere. It's not about oceanic crust or continental crust. Lithosphere may contain oceanic crust also on one side. Okay? There the oceanic floor is assumed to be totally static. Here the oceanic floor is continuously moving. They accept the seafloor spreading theory. There the movement of these continents, okay, there only the continental movement was assumed. The movement of continents, it was done in a manner that it causes no deformations at all. It was assumed that it offers almost negligible resistance. It moves without much resistance. That is the term he used. Continental drift theory believe that the continents are capable of moving without much resistance. But plate tectonics believe that there is a strong resistance offered by the plates. Particularly along the plate boundaries, there is a strong resistance offered. Whenever there is a resistance offered, it undergoes deformation. Changes along the plate boundary. That is why all of this will happen. Fold mountain, volcanism, earthquakes, tsunami. Okay, many of these are because of that only, deformations which are causing the resistance, higher resistance offered by the plates during their motion. If it is moving very smoothly without any kind of changes, so it will remain the same. It will not undergo changes as such. So basically the entire region of lithosphere, which is made up of different plates, they are in continuous motion with respect to asthenosphere. And this motion causes deformation along the different parts, creating different things, different types of landforms. It results in the creation of new landforms, is that right? Therefore the word tectonics. Plate tectonics is the study of landforms created by the plate movement. Plate tectonics. The study of all the different type of deformities and landforms created by the movement of plates. Plate tectonics. तो बेसिक आइडिया तो यही है, ठीक है? So when we talk about the plate boundaries, we have to go in detail. How many different types of plate boundaries are seen here? How many different types of plate boundaries are there in total? 3 or 3? 3 into 3. So within that, again, depending upon the margin, let's say divergence, we have ocean divergence, continent divergence. Convergence, ocean convergence, continent convergence, like this. So total how many, including all of this? 9 नहीं है क्या? 3 into 3. 6. कैसे? Among the divergent plate boundary, there are only 2 types of divergence. One is ocean divergence or continent divergence. There is no ocean continent divergence. Among the convergence, we have 3. Among the transform, it is the same. There is not much of difference at all. Ocean, continent, everywhere transform is same. ज़्यादा कुछ फर्क नहीं पड़ता है. Therefore, a total of 6 type of plate boundaries. Let's study them in detail. Starting from number 1, ocean divergence. An ocean divergent plate boundary is where two oceanic plate margins are moving away from each other. Remember the word plate margin. I'm not saying plate. It is not necessary that entire plate has to be oceanic plate. Completely oceanic plate तो एक ही है, वो है हमारा Pacific plate. बाकी में oceanic भी होगा, land भी होगा, continental भी होगा. There is no exclusive continental plate. When two such parts are moving away from each other, when two such margins of plates are moving away from each other, that kind of boundary is what is called as ocean divergent plate boundary. What exactly happens along the ocean divergent plate boundary? So this is the rising magma. There's more amount of magma coming through this part where there is mid-oceanic ridge, where there is crack in the oceanic floor. Why? What is the reason behind this? Okay, so if the pressure is released, why more magma? Temperature difference is there between these two parts. Okay, almost same. Anything else? Wherever there is a crack, the oceanic floor, the entire plate thickness is small. You can see mid-oceanic ridge, iska sides dekho, and very small. Because of which the overall pressure exerted by these part of the lithosphere on this area is less. It exerts lower pressure here. Lower pressure, lower melting point. The rocks melt faster here. One of the important reasons behind the magma generation along the mid-oceanic ridges. Other than this, of course, rising currents of magma. There are huge currents of magma which is rising from below. It is because of this only the magma is rising up. Okay? So what is ocean divergence? There is a crack in the oceanic floor. From this crack, the magma is trying to come out continuously. As it comes out, it gets accumulated on both the sides. It gets attached and it solidifies and it will push the older ones away. The older rocks are getting pushed away. The newer rocks are formed at the mid-oceanic ridge. ये तो कहीं पे सुना है? Sea floor spreading theory. वहाँ से directly copy कर दिया इन लोगों ने. The difference is there they say sea floor is moving. Okay, so oceanic floor is moving. The magma is trying to come out. Here they say the plate is moving. The entire plate will move as long as its boundary is there. So this entire part. The entire plate is moving actually. It's not about the crust, whether it is continental crust, oceanic crust, usse farak nahi padta hai. It has to be the part of the same plate. And there is the same plate on both the sides. It moves. Here the movement is also supported by asthenosphere, which is semi-solid, semi-liquid in nature, and near to the crack it is the asthenosphere which is melting faster, providing more magma. Okay, here it is providing more magma, which is pushing these parts continuously away. It is because of this the seafloor is spreading. So don't think the seafloor is spreading, therefore the magma is coming up here. It is actually other way. First the magma comes up, first it forms the crack in the oceanic floor, then it starts to spread. यहाँ से बाहर आने के पहले यहाँ पर भी होना चाहिए ना. There should be continuously rising magma which is capable of cracking through the lithosphere and pushing them continuously apart from each other. As they get pushed away from each other, new oceanic floor is formed between them. Older one is getting pushed away. So basically wherever there is ocean-ocean divergent plate boundary, in between there is a construction of material. Which material? Plate material. Therefore ocean-ocean divergent plate boundary or any divergent plate boundary is called as constructive plate margin. Constructive plate margin. Creates new oceanic crust. Whenever two different parts the plates are interacting, whether it is divergence or convergence, there is stronger friction between the different rock layers. When I say one plate, how thick the plate is? Nearly 100 kilometers. 100 kilometers thick sequence of rocks are there. When they are moving away, when they are moving towards, okay, so they are thrusting against each other, they are rubbing against each other, or they are just sliding past each other. Always there is a chance of buildup of energy. 100 kilometers of solid rocks. As they move, as they interact with each other, energy starts to build up. As energy starts to build up, there are chances that they may snap. Two different parts are moving like this, they're sliding like this. In between, continuously energy builds up and then suddenly snaps. That causes earthquakes. The plate interactions along the plate margins, wherever the plates are interacting, whether divergence or convergence or transform, it always produces earthquakes. Now earthquakes are divided into three types. Shallow, up to 70 kilometers, intermediate, between 70 to 360, deep, more than 350. Near divergent plate boundary, there is only shallow earthquakes. Because all the interaction is happening near to the surface only. If there is subduction, there is pressing down, then there are chances. Examples: Mid-Atlantic Ridge, Carlsberg Ridge. Where is Carlsberg Ridge? Indian Ocean. Can you see this part? There's a mid-oceanic ridge here. This is moving in this direction, this is in this direction. Carlsberg Ridge. East Pacific rise. Rise and ridge are almost same. Rise is slightly lower in elevation than ridge. This is between Pacific plate and Nazca plate. Around Nazca plate and between Pacific plate there is a ridge which is divergent in nature. It's called as East Pacific rise. RISE, rise. This is ocean-ocean divergence. In prelims, examples are very important, or otherwise the characteristics of the plate boundary. What do you observe, what do you not observe? Doubts here? Continent-continent divergence. There it is, continent-continent divergence. So what caused the divergence of oceanic part? What is the reason behind the divergence? Divergence. Rising currents of magma. If there were no magma, there would not have been a plate margin only. This entire part would have been part of single plate. Earlier it was a single plate only. When magma starts to rise from here, it causes the thinning of these edges, it creates a crack, and then it starts to come out. It starts with this rising magma. That can happen anywhere in the Earth's interior. If it starts to rise along the oceanic floor, it causes ocean-ocean divergence. If it starts to rise along the continental floor, it causes continent-continent divergence. So large currents of magma which rises from below, it is capable of cracking the entire lithospheric plate. उसको पूरा crack कर देगा. It'll crack it open. Once it cracks it open, in between the magma starts to come up, it will push both the sides apart gradually. It causes divergence. Both the sides, divergence. And the same thing happens over the continent. There it creates continent-continent divergence. However, this involves 3 stages. Continent-continent divergence involves 3 stages. The first stage is intracontinental rifting. Rifting is cracking. Intra is within. Earlier there was a single continent here. This is a total single continental plate. Don't say continent. Continental plate. Continental plate had completely continent above. Pura continent tha. Below that there was upper part of upper mantle. Okay, at least where it is happening, there was completely continent. Now this rising magma, okay, as I told you, it can happen anywhere. This continuously rising magma started to crack this continent over a period of time. It will break the continent into two parts. Magma is so hot, it is capable of doing that. Over a long period of time, this part gets separated from this part. From the upper part, if you see, there is cracks very clearly visible. This cracked part is what is called as Rift Valley. Okay, so here the magma is rising. Earlier it was a single continuous continent. It is the rising currents of magma which broke this. इसको break करके rift बना दिया. Since the upper part rifts and cracks and some part collapses, there is a series of faults. Because continental crust, when it breaks, it will not break uniformly. It gets broken into different blocks with cracks in between. Multiple series of faults are formed all along its length. Some of them normal faults, some of them reverse faults, multiple type of faults can be found. Okay, so you will see a continuous series of transform faults and other type of faults which we call it as the Rift Valley. This is completely Rift Valley. ये पूरा देखो यहाँ से लेके Rift Valley is also very active because here and there the magma is coming up. Magma has started to come up through the cracks and gaps here. ठीक है? Best example is East African Rift Valley. The entire eastern part of Africa is cracking right now. It is in the first stage. What is the name of first stage? Intracontinental rifting. This entire part is rifting and cracking. Okay, so here, like this. Because of this magma eruption which is happening here and there, you will find many volcanoes here. Many of these were earlier volcanoes. Kilimanjaro, Mount Kenya, they're all volcanic. And in many of these cracks, many of these depressions, huge amount of water has got collected. It has become lakes. Many of these are very big sized lakes are there in East African Rift Valley. After a long period of time, this will enter the second stage. What is the second stage? Okay, observe here. This continuously rising magma, because of its high temperature, it will start to melt both the sides like this. Both the sides of the continent will get melted. Over a long period of time, it becomes thinner like this. This has become thinner. Edge of the continent has become thinner. It has not only become thinner, it has also widened. The Rift Valley has widened. Okay, the depression has widened over a period of time. Like this. In this depression, the rising magma fills little bit. Because as this rising magma comes and accumulates here, it cools and solidifies, right? Okay, this is the magma which is still rising. It is not only rising, it is also trying to push both the sides continuously apart. This was a single continent. Now it becomes two separate continents. Both of them are being pushed apart by this rising magma. It is rising and pushing both the sides apart. Here it has solidified a little bit. Here you see the formation of a sea. Shallow sea. Because once the Rift Valley widens from one side, कोई एक साइड से तो पानी एंटर करेगा, ओशन वाटर कम्स एंड फिल्स दिस एंटायर डिप्रेशन, creates a sea. East African Rift Valley is going to get filled by ocean water from the Indian Ocean in few million years. That will completely cut off this eastern part from the rest of Africa. This is the part which is rifting, first stage of rifting. This is the second stage. Can you see? The entire Arabian Peninsula is in second stage. Earlier this was part of Africa. First a rift valley developed here. The same way there is a rift valley here, a rift valley developed here. As it entered the second stage, both the parts of the continent has widened, it has got pushed away. The edges have become thinner, and in between, the ocean water has entered. It has resulted in the formation of a sea, a Red Sea. Okay, so Red Sea is in second stage. There's still, can you see this crack? There is still magma eruption happening over there. Just trying to push both the sides apart from each other. The rising magma from here, it is trying to push both the sides apart. There's continuous volcanic eruption happening at the floor of Red Sea. After, so second stages, interplate thinning. Now interplate thinning has happened, the oceanic floor, both the sides have widened up, and then both the sides are continuously moving away. Over a long period of time, imagine somewhat to be like this. Here there was a sea in between. Over a long period of time, this moves sufficiently apart. This also moves sufficiently apart. Why? Because in between, a new sea floor is building up. Because here the magma is rising up and it is cooling here and solidifying and pushing both the sides continuously apart, right? This pushing will cause them to move away. In between, the magma is continuously cooling and solidifying, building the oceanic floor. Why oceanic floor? Why not continental crust? Continental crust, the rocks are very much lighter in density. The magma is coming from the lower part of the earth. It is higher in density. It builds up only oceanic floor. Basaltic rocks, oceanic floor comes up. This is completely newly formed oceanic floor. Here the magma is still rising. The exactly same place where the magma was coming earlier, it is in the same place, only magma is still rising. This was the continental crust moving away, continental crust moving away. There is a newly formed oceanic floor spreading here, newly formed oceanic floor spreading here. In between, you see the formation of a mid-oceanic ridge here. This is what is third stage, formation of mid-oceanic ridge, MOR. The best example for this is the Atlantic Ocean and the mid-Atlantic ridge. Okay, so now imagine. Can you see this crack? This is where South America was earlier. This was Africa earlier. In fact, Africa had this entire Arabia attached. In the first stage of this continent divergence, this was a single part of the continent, right? In the first stage, both the sides started to move away from each other. A huge rift was developed. The rift started to push both the sides apart. Initially, it was a single continent. The development of a rift will crack the land here and will start to push both the sides apart. Gradually, the rift widens, a sea gets developed. This is what explained by Alfred Wegener. A north-south rift develops. Okay, north-south rift, here there was Eurasia, here there was North America. North America gets pushed here, Eurasia gets pushed over there. As the rift was developed, as the rift was widened, a new sea emerges here. And now this new sea will start to widen up. जितना ये widen होते जाएगा, इतना ये push होते जाएगा. Africa has moved from here to there. South America has moved from here to here. In between, entirely new oceanic floor has got created. The ridge is developed at the center. Therefore, the formation of mid-oceanic ridge. Why the ridges are at the central? It is at that point both the continents have moved away. It is not like there was an oceanic floor at the central part, the ridge has got created. It is from the ridge the oceanic floor was created. Therefore, it is at the center. Is that clear? Best example is the mid-Atlantic ridge. So this clears the doubt of Alfred Wegener. Alfred Wegener could not explain the movement of continents because he did not know the mechanism of seafloor spreading. Seafloor spreading says that seafloor was spreading. Now, what does the plate tectonics has added? Plate tectonics says that it is not just continent moving, it is not just seafloor moving, it is both of them moving. Because both of them are part of a plate. It is the plate which is moving. It doesn't matter whether it is an oceanic plate or continental plate, but plates are moving. Okay, so along the movement, if there is a divergence of ocean, it causes seafloor spreading. If there is a divergence of continent, it causes the drifting of continent. मैंने plate tectonics तो दोनों को explain कर दिया अभी. So now there was a single supercontinent Pangaea. This single supercontinent breakup happened around 280 million years ago. Huge rift developed between the northern and southern part. First stage of continent divergence. The rift widened, a sea was developed. कौन सा? Tethys Sea. It got separated into Angara Land, Gondwana Land. Okay, now further more rift developed, more continents started to move away. What caused the continental drifting? Continent-continent divergence. In between, ocean-ocean divergence also got added. So third stage of continent-continent divergence is ocean-ocean divergence only. Basically, divergence is the reason behind the continental drift. Is that right? Now, divergence clearly very well explains the drifting of continents. Now, if the continents are continuously moving away, all the continents were here, it got separated and then they're starting to move away. Okay, how long can they move? After some time, they have to converge only, no? If these are the continents which got separated and started to move here. Okay, so and behind that there is oceanic crust, right? These were the continents. ये सारा continent यहाँ पर था. Okay, so imagine all the continents were here. They start to move away because of ocean-ocean divergence. As they start to move away, what happens to the oceanic part here? If continents are moving away, it will push the oceanic floor towards each other. There is ocean-ocean convergence. Divergence on one side causes convergence in another side. There's convergence of plates. That is convergent plate boundary. Yes, right now it is widening. Yes, that's right. It may stop in the future. We don't know. That depends upon the strength of the currents which are rising up. Okay, just give me 5 minutes of break. Okay, so we'll continue. So, convergent plate boundary. So when two different plate margins converge towards each other, it causes subduction. So basically, when the plates converge towards each other, let's say this is one plate moving in this direction, there's another plate moving in this direction. It is trying to push. It is trying to push. If the force is something which is limited, the plates undergo slight deformation like this. It undergoes folding and it stops. But this is a continuous and prolonged force. It is continuous and prolonged. थोड़ा सा डिफॉर्म होने से काम नहीं चलेगा, फिर भी तो पुश होता ही रहेगा. And these are like very thick sequence of rock, 100 kilometer thick sequence of rocks. You cannot push them above. ये नहीं कर सकते हो उसको ऊपर भेज दो. Only possible way is this will push this plate down, or this will push this plate down. Both are floating above the asthenosphere, is that right? Here comes isostasy. Both are floating above asthenosphere, both are trying to move towards each other. The movement of one of them will push the other downwards. Now, which one gets pushed downwards depends upon the buoyancy force of the other plate. Which one gets pushed downward? A lighter plate experiences stronger buoyancy. Heavier plate experiences lighter buoyancy. Buoyancy force? जितना lighter है उतना वो floating होता है ना. Heavier है तो sink हो जाएगा. Let's say this is lighter and this is slightly denser. This has a greater buoyancy. This has a lesser buoyancy. When this plate tries to push this plate downwards, this will not get pushed downwards. बहुत जोर से उसको दबाने का कोशिश करो और जोर से ऊपर आएगा. Okay, so like for example, you take a plank of wooden plank, put it over the water, it floats. You try to push it down, ऐसे फोर्सफुली इसको नीचे डुबाने की कोशिश करो, जितना फोर्स लगाओगे उससे ऑपोजिट फोर्स आएगा. A lighter plate will not undergo, it will not get pushed down very easily. Compared to this undergoes pushed down very easily. ये थोड़ा सा डेंसर है, उसको थोड़ा सा दबाओ, ग्रेजुअली क्या होगा, अपना मूवमेंट भी है, इस साइड में फोर्स भी है, इसके वजह से ओवर ए पीरियड ऑफ टाइम ये नीचे दब जाएगा, नीचे मूवमेंट में आ जाता है. It gets pushed down and starts to move down. That process is called as subduction. Whenever two plates converge towards each other, the plate of higher density undergoes subduction below the plate of lower density. You have heard the story, but have you asked why? It is because of buoyancy. The plate of lower density experiences and exerts higher buoyancy. So this will not undergo subduction, rather it will push the other plate downwards. Gradually other plate will slide downwards and it will start to move downwards. इसको बोलेंगे हम buoyancy force. When two different plate margins are converging, if both are oceanic plate, both are of almost same density, but still there is some difference among themselves. Whichever is denser, that undergoes subduction. If both are of the same nature as it is, the older ones undergoes subduction. Older one always undergoes subduction because it contains higher sedimentary deposition. Okay? When it undergoes subduction, there comes ocean convergent plate boundary. The converging plate will undergo subduction. What do you mean by subduction? One of the plate will start to move down below another. As it moves down, it is going into which part? Asthenosphere. Asthenosphere is very hot, high temperature. It will start to melt this plate gradually. It will start to melt and this plate starts to become integrated into asthenosphere. It will become part of the asthenosphere gradually. Over a period of time, देखो. There the asthenosphere had supplied material. Here it is taking the material. There is a balance. Here it was creating new oceanic plate. Here it is destroying the oceanic plate. Therefore, this kind of plate boundary is called as destructive plate boundary. This is the other oceanic plate which is not undergoing subduction. Along the margin, if you see, there is a huge depression on the oceanic floor. And two plates converge at the zone of convergence at here. Normally, jitna oceanic depth hai, usse bahut niche hoga. Okay, if this is the oceanic plate which is above, this is the oceanic plate which is below. This is subducting. Can you see this depth? If this is the water surface, from the normal water surface, this is very, very deep. In fact, many of the times this is double. This part is what is called as trench. It extends all the way along the plate margin where there is subduction happening. Trenches are generated. Trenches are always found near to the zones of subduction. As the plates undergo subduction, this entire zone is called a subduction zone. The rocks of this plate is undergoing intense compression. They are highly getting compressed. पूरा ऐसे दबा रहे हैं इसको. Temperature is changing, pressure is changing. It is undergoing metamorphism. Right? Over a long distance of subduction, it undergoes complete melting. It will take 700-800 kilometers. What is the thickness of a lithosphere? 100 kilometers. It goes up to 700-800 kilometers into the asthenosphere, then it completely gets melted down. But before this, there are certain changes happening. The rocks are intensely getting compressed. Temperature is rising. They are undergoing metamorphism. During this process, some of the rocks will start to melt. Some of them, within this entire lithosphere, some of the rocks will start to melt. Those rocks which are of usually lower density, lower melting point. जिसका melting point थोड़ा सा कम है ना, so this is made up of large number of different types of rocks. Some of them which are made up of lower melting point, they start to melt fast. This process is called as partial melting. पूरा lithosphere melt नहीं हुआ है. Only some part of it is melting and releasing magma. This releasing magma is made up of lighter density material. Okay, so because they are melting fast, lighter density material जल्दी जल्दी melt हो रहा है ना, so वही lighter density में इतना जल्दी melt होता है. As this material is producing magma, this magma because of lower density, it starts to rise up. ऊपर आना शुरू होता है. First it comes and accumulates in the other oceanic crust. Other lithosphere, other plate के अंदर जाके accumulate होगा. But here the magma is continuously being produced. Over a period of time, it just continuously builds up, pressure builds up, and then finally erupts on the oceanic floor. This continuous eruption happens. Over a long period of time, it builds up. Initially, they are below the water only. It creates volcanic mountains below the water. It creates volcanic mountain below the water. They are called as sea mounts. Volcanoes, totally, okay, they are erupting. Over a long period of time when they continuously erupt and they continuously build, they rise above the water also. When such volcanic mountains comes above the water, that is what we call it as volcanic islands. Okay, volcanic islands are like submerged volcanic mountains. Many of them are still active, erupting magma. So like this, next to the trench, you will see a continuous chain of volcanoes in a continuous line next to the trench. Right? Usually a trench is arc shape because the force of the plate movement is not uniform everywhere. In some places it moves fast, another places it moves overall, it takes an arc shape. Since the trench is arc shape, this island is also arc shape. The continuous line of islands, it's called as, it's in arc shape. What is it called as? Island arc. It results in the formation of island arc. If the magma which is generated is undergoing due to intense melting, there's an intense generation of magma. You know, sometimes there's more lighter material, it is generated in a large scale. Okay, or faster subduction is happening, melting is happening at a faster rate. Huge amount of magma comes up everywhere. Large group of islands are formed. When such large group of scattered islands are formed in the ocean, the entire group is what is called as archipelago. All of these are formed along the ocean convergent plate boundary. During this process of subduction, there is continuous friction between the rocks. One of the strongest friction happens. You know, it is not very easy to thrust this plate downwards. There's one plate, below that you are pushing another plate. These plates offer a very high resistance. As they get pushed down, thrust down, the energy continuously builds up. As the energy continuously builds up, there are higher chances that they snap. Energy builds up, snap. Energy builds up, snaps. That is how it goes. Do you think they are smoothly moving? Never. These are hard rocks. Okay, so as they move, they get stuck. Energy, once it builds up, then it slips. They get stuck, slip. Stuck, slip manner. Continuously earthquakes are generated. One of the most intense earthquakes are generated here. At what depth? All the depth. Shallow, intermediate, deep-seated. Subduction zones provides most intense, most frequent, and all the type of earthquakes. However, there are certain zones where you find most frequent earthquakes. There are certain zones where you find most frequent earthquakes. Why? Because, you know, here the tension is just building up. Here there is less tension because it is melting. In between there is a very high zone of tension. Frequent friction. There large number of earthquakes are produced. This zone where a frequent earthquakes large number are produced, they are called as Benioff zone. Benioff zones are the zones along the subducting plate near to the subduction where we find one of the most frequent and intense earthquakes. So बताइए एक बार sequence ocean convergence. The plate of higher density subducts below the plate of lower density. Subduction creates subduction zone trenches. And after certain depth, it will completely melt, become part of asthenosphere. But in between, the rocks are undergoing intense compression, metamorphism, partial melting. Partial melting generates magma. Magma generation causes the lighter material to rise up. This lighter material, as it rises up, it accumulates on the other oceanic plate. It comes out on the oceanic floor, builds up sea mounts, volcanic mountains. It rises through height, becomes volcanic islands. Okay, large number of islands arranged in arc shape, island arc. Large group of islands dispersed, spread out in the ocean, archipelago. Earthquake happens at Benioff zone, more frequent earthquakes. All the depths, shallow, intermediate, deep. Okay, so everywhere होगा, but सबसे ज़्यादा Benioff में होगा. And the same kind of convergence happens along the ocean continent margin. It results in ocean continent convergence. That is also a destructive plate boundary. Everything is almost same. Okay, so except 2-3 events. Here it is very clear that the oceanic plate is having higher density, it undergoes subduction. Continental plate with much lower density, it will push the oceanic plate downward very, very easily. Because the buoyancy of continental plate is higher. It is the same buoyancy of the continental plate which is offering a stronger resistance will cause it to undergo deformation like this. The entire edge of the continents undergo deformation. यहाँ पर तो easily allow कर दिया था because overall force of buoyancy is low. Here the stronger force of buoyancy by the continental crust will try to offer a stronger resistance. In the process, it undergoes deformation. The entire edge of the continents undergoes folding. Entirely along the edge, you will see the formation of fold mountains. Okay, so totally fold mountains. Here the oceanic plate is subducting. Subducting produces subduction zone, trenches. Here also trenches are there. Okay, so there is a partial melting, metamorphism, partial melting, complete melting, all of these are happening. There's Benioff zone, earthquakes are produced here, everywhere. The magma is being produced, but this time magma accumulates on the continental crust. There it had accumulated on the oceanic crust. There it resulted in the formation of islands. Here there is no island, already it's continent. It rises through the continent, it comes out of it, the magma erupts out on the fold mountains. Now the fold mountains, they will have volcanoes. On top of fold mountains, there are volcanoes. Best example, not Himalayas, Andes, Rockies. Okay, so in Deccan Plateau भी अलग है, उसका अलग concept बताता हूँ. Can you see here? This is the Nazca plate, which is subducting below South American plate. This is a minor plate, Nazca plate. This is subducting below South American plate. This compression has created a trench here. Can you see this Peru-Chile trench here? You can very clearly see this dark line. Is that right? The entire edge of this South American continent has got folded. That has resulted in the formation of Andes mountains. from the southernmost to the northernmost point. The longest mountain chain in the entire world on the continent. Much, much longer than Himalayas. Okay, there is subduction happening. There is a subduction zone, partial melting, magma generation. This magma is accumulating and rising on the continent. Everywhere there is continuous volcanoes here. One of the most active volcanoes on the surface of Earth. One of the tallest active volcanoes on the surface of Earth. The tallest active volcano in the world is Ojos del Salado. Have you heard? Ojos del Salado. Here, along the Argentina border. Cotopaxi, Chimborazo, they're all active volcanoes in Ecuador. Continuous line of active volcanoes. One of the important zones of volcanic eruptions and earthquakes. यही major difference है. Formation of fold mountains and volcanic eruptions over the continent. That is the major difference between ocean-ocean convergence and ocean-continent convergence. Rest everything is same. Next comes continent-continent convergence. See, for two continental parts to converge, first the oceanic parts should completely get subducted. मैंने यहाँ पर दिखाया था. Continents सारा यहाँ पर था. It started to drift away. Because of this, इसके पीछे जो oceanic crust था वो converge होना शुरू हुआ था. Starts with ocean-ocean convergence. मान लो एक साइड से पूरा ओशन खत्म हो गया, कन्वर्ज होते होते खत्म हो गया, फिर कॉन्टिनेंट आना शुरू होता है. देन देयर इज ओशन कॉन्टिनेंट कन्वर्जेंस. फिर ये वाला ओशनिक प्लेट भी खत्म हो गया, फिर आएगा कॉन्टिनेंट कॉन्टिनेंट कन्वर्जेंस. इज इट राइट? Continent convergence always begins with ocean continent convergence. You can never break a single continent into two parts and ask them to undergo convergence. ऐसे तो mechanism नहीं है. Okay, so you break single continent into two parts, you move them apart, sufficiently apart, and after some time they converge. In between, the oceanic crust has to undergo subduction. There's always oceanic crust in between. So therefore, continent convergence always begins with ocean-continent convergence. I said this was the continental crust, this was the oceanic continental plate, oceanic plate. Oceanic plate was undergoing subduction. Okay, there was a continental plate here. Okay, this was the continental plate, this was the oceanic plate. They are moving like this. This was the continental plate moving like this. Before these two continents converge together, this oceanic plate has to undergo subduction. When it completely undergoes subduction, then the continent-continent convergence begins. It's always the ocean-continent convergence which occurs before the continent-continent convergence. What is happening? There is a trench formation, there is a volcanic eruption. Okay, so this volcanic eruption generates the volcanoes. Okay, sometimes magma flows, creates volcanic plateau. Okay, there is a fold mountains. Okay, because of compression, all of this is happening. Right? And this is undergoing subduction. There is subduction zone, Benioff zone, trench formation. Okay, so there's shallow, intermediate, deep-seated earthquakes, magma accumulation, everything is happening. But after some time, when this entire oceanic part continues completely undergoes subduction, okay, पूरा के पूरा subduct होके खत्म हो गया.
Then the continent-continent convergence begins. After sufficient convergence, you will see, because there is a limit to this part. When everything undergoes complete subduction, the continental part is here. This is the other continental part, which has undergone folding, all of these changes that happened. This part is there as it is. This is the continental part. Now this continental part is converging here. What happens to this layer of volcanism, all of this, that is still there. But the generation of magma has stopped. The generation of magma will continue as long as there is subduction. But after some time, subduction has to stop. When subduction stops, magma generation stops. Subduction will be there as long as there is oceanic crust left, oceanic plate left. Continuous movement will cause the entire oceanic plate to undergo subduction. Gradually, entire oceanic part gets detached from the continental. However, this movement will drag a part of the continent downwards. इसको drag करके नीचे तक लेके आएगा, थोड़ा सा. The initial movement will drag some part of it. Therefore, there is some partial subduction of this continental part. But after certain depth, it cannot undergo further subduction. Why? ये तो continental plate है. Continental plate never undergoes subduction. उसको बाद में realize हो गया, मैं तो continental plate हूँ, मैं क्यों subduction हो रहा हूँ? तो रुक जाओ. Because of stronger buoyancy, it will stop it from further subduction. अभी जितना भी push करो, ये subduction होगा ही नहीं. It is not possible. The continued convergence causes both the continental crust, both the continental plate to get stitched together. इतना जोर से यहाँ पर दबाओ, दोनों jam हो जाएगा. Both of them get stitched together. It creates a zone where both the continents have got stitched together, which is called as suture zone. Suture zone is created now. What happened to the oceanic plate? Everything is gone. Everything is subducted. But however, there is a force which is trying to push both of them even now. अभी भी पीछे force है. पीछे force क्या है? पीछे force ये है कि एक ridge है. Ridge is like engine. Okay, इसके पीछे कोई ridge है, इसलिए दबाते जा रहे हैं. It is still trying to push it. In the meantime, something happens. What happens? During this entire process, huge amount of sediments gets accumulated in this region. What sediments? The sediments derived from both the continents. Here there is a continental crust, rivers are coming, winds are coming, glaciers are coming, huge sediments are deposited. On the other side, there is continental crust. Okay, so huge accumulation of sediments happens and the entire basin is contracting. Gradually, the thickness of these sediments will increase. Over a long period of time, a huge sedimentary basin gets developed. All the sediments accumulate together and forms a thick sedimentary basin in between. Okay, so this entire basin will get filled with the sediment. Sediments were there from both the sides. Because the entire basin, as it is contracting, the thickness of the sediments will start to increase. Earlier it was all spread up, now it is coming closer. Thick basin is formed. Now you try to push both of them. This continental crust is trying to push, this continental crust is also trying to push. The result of this compression comes on this sedimentary layers. जब दोनों को दबाने का कोशिश करो, ये फोर्स क्या करेगा? इन दोनों के बीच में सेडिमेंटरी लेयर है ना, उसको दबा देगा. ये तो बहुत इजीली दब जाएगा. It undergoes very easy folding because it's a sedimentary layer. Okay, sedimentary layer undergoes easy folding. This compression causes the sedimentary layer to undergo folding like this. A tall, young fold mountains are formed here. They are going to be very, very tall. Why? This is formed on top of the continent. Not single continent, two continent. Where two continents have already merged together, forming a thick mass. On top of this, there is a fold mountain formation. Second, the nature of the rocks. The nature of the rocks are completely sedimentary in nature. When you fold them, it causes the formation of steep mountains. बहुत आराम से fold हो जाएगा ये. Harder and resistant rocks will not undergo folding. Sedimentary layers undergo easy folding, because of which it forms very steep and tall mountains. Recently formed, therefore, young fold mountains. They are totally non-volcanic. देखो इसीलिए color यहाँ पर change है, यहाँ पर change है. This was volcanic in nature. Volcanic eruption had happened. Abhi now it is cut off, but volcanic material is still there. Solidified rocks. It is totally free from volcanism. This is made up of sediment from the ocean. कौन सी ocean? इसके बीच में जो ocean था ना, marine sediments. Many of the marine sediments are marine fossils are still there. You go to Himalayas, you will find many of the marine fossils over there. As long as this is compression happening, these fold mountains are continuously rising. Okay, it will continue to rise as long as the compression is happening, because subduction cannot happen. After a long period of time, compression will stop, because it has to stop. It ends with continent-continent convergence. When both the parts are completely merged together, it becomes a single continent. Then this upliftment will stop. Okay, so once it has become a single continent, now the entire continent will start to move together, no? Earlier, now there's this convergence. That can happen as long as there's an active plate boundary here. Now there is no active plate boundary here, everything is merged together. Now both the resultant force will push in one direction. Entire part will start to move. Now both the continents are of same part, single part. Best example is the Himalayan formations. The Indian plate started to move towards Eurasian plate. In between there was Tethys Sea. Tethys Sea had a oceanic plate. Oceanic plates below that Tethys Sea. That oceanic plate of Tethys Sea was undergoing subduction. The subduction released magma through partial melting, which got erupted on the Eurasian side. There was folding had happened. There was formation of volcanic mountains. Tibetan Plateau. Tibetan Plateau is totally volcanic in nature. Ladakh is volcanic in nature. Karakoram is volcanic in nature. All of these are earlier formed mountains. After some time, the entire Tethys Sea contracts. Entire Tethys Sea contracted. The sediments deposited in the Tethys Sea over a period of time become a huge sedimentary basin. Tethys sedimentary basin. This Tethys sedimentary basin will start to undergo compression. In the meantime, Indian continental plate undergoes partial subduction. There is a formation of suture zone between Indian continental plate and Eurasian continental plate. The entire sedimentary basin will undergo folding. That folding results in the formation of Himalayas. Himalayas are the tallest fold mountains in the world. Why? Because it is formed along the continent-continent convergence plate boundary. It is located on top of the continent. They are totally free from volcanic material. There are no volcanoes in Himalayas. They are totally made up of marine sediments derived from the ocean bottom, filled with marine fossils. Many of the marine fossils of older time, पुराना time का marine fossils अभी Himalayas में मिलता है. Many of them are mollusk, shell-based organisms. के rocks के अंदर मिलते हैं fossils. And the convergence is still happening. The Himalayas are still growing. हमने शुरू किया था continent divergence से. Continent divergence happened. Gradually it resulted in the creation of new oceanic floor in between. Ocean divergence happened. This continued divergence caused the ocean convergence. When one of the plate completely got subducted, ocean-continent convergence. When both the oceanic plate got completed, continent convergence. Now both of them are merged together. शुरू यहाँ से करके फिर यहाँ पर आके खत्म कर दिया हमने. This is what is Wilson cycle. What is a Wilson cycle? Continuous cyclical manner, the plate's boundaries keep changing. See here, Continent divergence, right? Rifting, all of this happened, sea formation, then the ocean divergence. After some time, one of the oceanic plate will start to undergo subduction, ocean convergence, ocean continent convergence. When this entire plate undergoes complete subduction, then again continent convergence, बीच में fold mountain बन गया, अभी दोनों एक ही हो गया. After a long time दोबारा यहाँ से शुरू होगा, यहाँ नहीं तो और कहीं पे शुरू होगा. The cyclical nature of change in the plate boundaries continuously is what is called as Wilson cycle. Which Wilson? The same J.T. Wilson, who gave the idea of plate. So what kind of earthquakes do you find along the continent divergence? Shallow earthquakes? Yes or no? Intermediate earthquakes? Continent convergence. Intermediate earthquakes also, because of partial subduction. But there are no deep-seated earthquakes, because there is no subduction. है ना? Volcanism तो है ही नहीं. A parallel plate boundary is where two plates slide past against each other. They are moving against each other. Here there is no destruction of plate. Plates are not getting destroyed. There is no construction of plate. Plates are not getting created because there is no magma eruption here. No subduction, no magma eruption. The plates just slide past against each other. They conserve each other. There is a conservative plate margin. Okay, so along this plate margin, there is no construction, no destruction, no volcanism, but there are strong earthquakes. One of the strong and most intense earthquakes. Because as they slide past against each other, there is a continuous friction between them. This friction continuously builds up, creating earthquakes on regular basis. All along this entire part. One of the most intense earthquakes are found here along the transform plate boundaries. That is what is happening along the San Andreas Fault. This is a picture of San Andreas Fault. Okay, where the Pacific plate is sliding against the North American plate parallelly, the parallel movement. So other than this, along the mid-oceanic ridges also in between, you will find the parallel plate boundary. Okay, can you see these two parts of the mid-oceanic ridge? There is one part of the mid-oceanic ridge, another part of the mid-oceanic ridge. Okay, so observe this carefully. This is a mid-oceanic ridge, this is a mid-oceanic ridge. Okay, here it is moving away, here it is moving away. This is a mid-oceanic ridge, moving away, moving away. Can you see in between? They are moving parallel to each other. Two different parts of a mid-oceanic ridge. Of course, it's the same mid-oceanic ridge only, but two different segments. Between two different segments, you will find a parallel plate boundary. It acts as an offset mechanism. Is it right? These are the plate boundaries. Now, what are the causes of plate motion? Overall, what is causing the plate motion? Endogenetic energy, energy from the Earth's interior. But that comes out in different forms. There are 5 major causes of plate motion. Number 1, convection current. The convection current theory was proposed by Arthur Holmes. Arthur Holmes gave this idea of convection currents. So what are convection currents? Convection currents are large scale movement of magma which is happening in the Earth's interior. They're like large scale currents of magma, either covering the entire mantle or only asthenosphere. Some of the currents are smaller, some of the currents are larger. Okay, so covers the either entire mantle or asthenosphere. They rise from below. As they rise from below, they hit the lithosphere. Okay, they rise from below and they hit the lithosphere. This lithosphere is acting like a hard and rigid outer cover. It will try to block. It will try to block the convection current. However, a part of it comes out, it flows out, creating a ridge over there. But most part of it gets diverged and moves away. These currents gets diverged and move away. As they move away, they flow below the lithosphere. Below the plates, they move, and as they move, they push the plates in this direction as well as this direction. When two such currents from opposite direction converge together, they converge and start to descend down. As they descend down, they drag the plate also. Tum bhi aa jao mere saath. And as they come here, they go back. This is a convection current. This is a convection current. Such kind of currents are there in the mantle, moving all the way, or maybe within the asthenosphere. Continuous cyclical movement. This continuous, very slow, very, very slow. Happens over a long period of time. Wherever they rise, there you see the cracking. If there is an oceanic crust here, it causes ocean-ocean divergence. If there is a continental crust here, it causes continent-continent divergence. Simple. Wherever they converge, it causes subduction. Ocean-ocean convergence, ocean-continent convergence, continent-continent convergence. Is that right? Major reason तो convection current ही है. इसी की वजह से major movement तो इसी की वजह से चल रहा है. ऐसे मानते हैं. कोई देखा तो नहीं. Okay, it is widely accepted, this theory, convection current theory. Second one is mantle plumes. What are mantle plumes? Mantle plumes are like jet-like plumes of magma. Okay, so it gets generated from the lowermost part of the mantle. Okay, if the heat generated from the outer core, which gets transferred to the mantle, melts the magma, melts the rocks. And this magma continuously rises up like a solid jet. Okay, jet जैसे, strong jet जैसे ऊपर आके hit करता है. They are not cyclical in nature. They are not currents. They are unidirectional. यहाँ से ऐसे आके ऐसे hit करता है. Wherever it hits the lithosphere, there it spreads out. It hits the lithosphere and then spreads out. A part of it cracks and then comes out, creates volcanoes over there. This is called as mantle plumes. Plumes of magma. What is the role of mantle plumes in plate motion? It transfers heat from lower part to the upper part and keeps the plates in active motion. Energy तो चाहिए. Energy तो चाहिए ना. That energy is transferred from the lower part to the upper part by this mechanism. And जैसे आके ऐसे hit करेगा, ऐसे push करेगा ना, it will push the plates also. It causes intra-plate movement. Convection currents causes movement along the boundaries, plate margins. This happens mainly along the intra-plate, within the plate. जहाँ पर भी hit करेगा, ऐसे extra push, extra energy, extra heat getting transferred. That is mantle plumes. Wherever there are mantle plumes, you will find volcanoes on top of it, which are called as hot spots. इसको हम बोलते हैं hot spots. Third one ridge push. Fourth one, gravity sliding. Fifth one, slab pull. Ridge push, gravity sliding, slab pull. All three are related. Wherever there are ridges, we experience a strong push away from the ridge. Why? The rising magma is pushing it away like this. The rising magma, which is wedging into the gap, becomes solidified and push the older ones away. That is what is called as ridge push, one of the strongest force. It is the ridge push only which is causing the plates to move away from the ridge. Sea floor spreading is happening. Ocean divergence, continent divergence, everything is because of a ridge push only. It's like an engine. Okay, only railway engine आगे रहता है, ये पीछे रहता है. पीछे से ऐसे धक्का देता रहता है. Ridge is always pushing in nature. If there is oceanic plate here and there is an oceanic plate, it starts to undergo convergence. इसके पीछे से धक्का दिया तो convergence हो जाएगा. On the other side, if there is a continent, ocean continent convergence. Okay, फिर इस side में continent है, उस side में भी continent है, continent convergence. Ridges are always responsible for that. Best example, why the Indian plate is converging with the Eurasian plate? Because of Carlsberg Ridge. Carlsberg Ridge is continuously pushing it. That is what is ridge push. Wherever there are ridges over a period of time become elevated. Due to continuous accumulation of magma, it increases its height. कभी कभी ये ऊपर आ जाते हैं, ओशन से भी ऊपर आता है. जैसे फॉर एग्जांपल हमारा आइसलैंड है. Iceland is part of mid-Atlantic ridge which is raised above the water. Okay, you can see mid-Atlantic ridge on top of land over there. इसलिए लोग जाते हैं आइसलैंड तक. Okay, on top of land you can see the mid-Atlantic ridge. So if you compare, there is a difference in the height between this part and this part. Normal oceanic floor and top of the ridge, there is a difference. There is a difference of gravity. The difference of gravity causes this part to slide in this direction. Okay, so like this. If plate is moving completely horizontal, you need some push. If it is moving obliquely, there's some gravity force. Near to the ridge, just gravity is also helping because of the difference of height. You know, there's this oblique motion, right? Gravity sliding. Gravity is also pushing the plate away. Trenches के पास में slab pull. What is a slab pull? As the subducting plate melts, it gets assimilated into the mantle. पूरा melt होके mantle के अंदर पूरा merge हो जाएगा. It happens at a very lower depth. बहुत नीचे जाके merge होगा. But as this melting is happening, it will make the plate little bit soft. It will make it fluid. Merge हो मतलब melt होते होते क्या हो रहा है? वो fluid nature में आ रहा है ना? It starts to flow faster. Here the movement of the plate increases because of its fluidity. Rigidity कम हो गया, fluidity ज़्यादा हो गया. And एक side में fluid होना शुरू हो गया, ये movement ज़्यादा आ गया, ये थोड़ा सा नीचे खींचता है ना? Because this is part of the single slab. Plate is called a slab here. The faster movement of the melting part causes the pull of this entire slab downwards. ऐसा लग रहा है इसको कोई खींच रहा है, अंदर खींच रहा है. Pulling down along the trenches. Slab pull is experienced along the trenches. यहां से खींचो पूरा slab तो निकल के आएगा ना? Because everything is a single part. That is slab pull. There are all the reasons behind the plate motion. What are the limitations of plate tectonics? There are few things which are not yet explained. Okay, this is convection current. You can see the convection currents. The rising currents causing ridge, the subsiding part causing subduction, trenches and subduction. Okay, there are few parts which are not yet explained. The plate boundaries in the past and the plate boundaries in the future. See, obviously the plate boundaries are not permanent. If you understand the mechanism, you clearly get to know. Plate boundaries are not permanent. नया प्लेट बाउंड्री कभी भी क्रिएट हो सकता है, पुराना प्लेट बाउंड्री कभी भी खत्म हो सकता है. What creates new plate boundaries? What causes the stopping of old plate boundaries? It is not very clearly understood. We know that fold mountains are usually formed along the plate margins, right? But there are many fold mountains which are found in the interior of the continent. For example, Aravallis, Appalachians. They are all the result of old plate boundaries. पुराना plate boundary तब convergence हुआ था, तब plate boundary active था. वो क्यों inactive हो गया? What were the earlier plate boundaries? Why did they become inactive? What happens to the present plate boundary later? Okay, how it is going to proceed? ये सारा अभी clear नहीं है. This is a limitation. The past and future of plate tectonics. What were the past plate boundaries? What will be the future? How the plate boundaries changes? Okay, how a divergent plate boundary stops? How a convergent plate boundary stops? ये थोड़ा सा clear नहीं है. What mechanism is responsible for that? So one more thing which is not very clear is what happens to the future of African plate and Eurasian Antarctica plate. African plate, can you say it is totally surrounded by ridges everywhere? That means African plate is continuously growing from every side. Along the ridges, the oceanic plate is getting added, right? So gradually African plate is continuously becoming bigger and bigger. How far it is going to go like this? We are not sure. Same is the case with Antarctica. You can see it is totally surrounded by ridges everywhere except a very small part here. Everywhere it is totally surrounded by ridges. Ridges are where the oceanic plate is continuously created. So the plate is continuously growing. How far it is going to grow? Okay, so to what extent? When will it stop? What makes it stop? What will change it? All these are not very clear. These are the limitations of plate tectonics.
Outer surface of our planet. It may look like one solid shell. But according to the theory of plate tectonics, this outer layer, called the lithosphere, is actually broken up into massive, rigid slabs called tectonic plates that fit together like puzzle pieces.
इतना गैप तो नहीं है, एनिमेशन में दिखा रहा है, ठीक है? Cannot have this kind of gaps, just the animation. But the plate boundaries are there actually.
Floating on a thick molten layer of the mantle called the asthenosphere. The plates slide around like slow-motion bumper cars, traveling up to 6 inches a year. Right now, Earth's crust is divided into 7 large plates and dozens of smaller ones. The boundaries between these plates are dynamic and violent places that make and break Earth's crust. The relative movement of the plates creates 3 types of boundaries. A divergent boundary occurs when 2 plates move away from each other. On land, you can easily see this. Diverging plates create huge troughs like the Great Rift Valley in Africa. If the spreading here continues, the Indian Ocean will eventually flood the rift, converting the entire eastern Horn of Africa into a massive island. Transform boundaries are where two plates grind past each other in opposite directions. The most famous example is the San Andreas Fault, where portions of Southern California, including Los Angeles, are sliding roughly 2 inches closer to Northern California each year. A convergent boundary, on the other hand, is where two plates collide. The impact often weakens and crumples the crust upward into jagged mountain ranges.
You've been working on in class. Let's get started. Obviously, you've been working on this theory called plate tectonics, which is basically an extension of Alfred Wegener's work. This theory that we're going to look at was put together in the mid-1900s and built upon what crust plates on. Here, this is our cubic table. With this that the on the is convex and cell right back. The plate mean and of the earth beat now when two plates interact boils down transform boundary and divergent things we see at each. This is a map and you're at this. Let's start with transform boundaries. So these are the boundaries where plates slide past one another. If you take a look at this animation, you'll notice the lithosphere floating on top of the asthenosphere is
This
being driven
indicates
by convection
earthquake.
currents, which is causing them to
Energy
slide
builds up and releases.
laterally
Energy
past
builds up,
each other,
releases.
right
That is
past each other.
earthquakes.
And so right along that boundary in the middle, you get a lot
And all of this is
pressure
limited
built
to
up,
the
a lot of
surface area only,
grinding
right?
of
So
the
they are all
plates,
shallow earthquakes.
which is often released in the form of earthquakes. Transform
Where
boundaries
there is no
very
subduction, you
commonly
can
have
expect
earthquakes.
you cannot
However, they
expect deeper
don't tend to
earthquakes.
have volcanoes. They don't tend to have major mountain ranges, and certainly not trenches. The only real feature we see at transform boundaries are earthquakes. This is an example of a place on Earth where you can actually see a transform boundary at the surface. This is known as the San Andreas Fault, and it's found in California. It's responsible for the big earthquake risk of cities like San Francisco and LA. Let's go back to our reference table for a minute here and see that the transform boundaries are shown down on the bottom with this symbol, shown in green here. There's a couple of them, not too many, but the most famous and important one would be the San Andreas Fault, shown right there. Again, if you forget how transform boundaries actually work, the arrows kind of reveal the motion, so it's a good tool to use your reference tables. Next type of plate boundary would be convergent boundaries. Now, these are a little more tricky because we have to consider not only the fact that two plates are coming together and colliding, but what type of crust is involved. For example, we see different things happening when it's oceanic crust colliding with oceanic crust, as opposed to when it's continental colliding with continental, and so forth. And so we have a few different types of convergent boundaries. The first type we call a subduction zone, and as you can tell by this little animation here, this happens when continental crust on the left collides with oceanic crust on the right. Now notice that the oceanic crust is sinking underneath the continental crust, and that's because oceanic crust is more dense than continental crust. It's heavier. And so when the two collide, the heavier oceanic crust sinks underneath the lighter continental crust. When it sinks, it melts because it's hot down in the asthenosphere. And that melting rock finds little cracks and crevices to rise through and ultimately erupts at the surface, forming active volcanoes. So some of the features we look for at subduction zones are a chain of tall mountains and active volcanoes, a deep ocean trench seen by this dark line just off the coast, as well as lots and lots of earthquakes, which tend to happen along that subducting plate. We also have island arcs. Now, very similar to a subduction zone. The only difference is that this is oceanic to oceanic, so no continents involved here. The one thing that's tricky is it's a little hard to tell which plate is going to subduct, being that they both have the same density. But eventually one plate, usually the older rock, will sink under the younger rock. And again, we will get this melting, which causes rising magma to create active volcanoes, which in this case form islands, volcanic islands, because we're talking about areas out in the middle of the ocean here. We also get a trench, which you can see clearly in the water there. And of course, we get lots of active earthquakes along the subducting plate.
What are the examples of island arcs? Japan Island Arc, Philippine Archipelago, Indonesia Archipelago. Okay, so Aleutian Island, Aleutian Trench bhi hai, Aleutian Island, Kuril Trench, Kuril Island. Okay, so and then these entire Pacific islands. Okay, so here we have the Indonesian, right, and the Caribbean islands. They're all island arcs. Okay, the result of ocean-continent convergence, ocean-ocean convergence.
Before I go back to the chart here, we also have a third type of convergent boundary called a collision zone, and that would be continental-continental. The best example of that would be India crashing into the Eurasian plate where the Himalayas are forming. But again, convergent boundaries, the Peruvian zone, the South America, the Andes Mountains, where three plates drift, the type of crust actually rips apart into
So this
two.
is the
What happens
process of
on land, we have what's called a rift
continent-continent
zone,
divergence.
where the land actually
Can you see the rift valley, cracked part? Gradually it becomes thinner and then it widens, then the sea is formed.
rips apart into two.
You can see the
We
formation of
see
sea.
this happening in
Then mid-oceanic
Eastern
ridges.
Africa right now at an area known as the East African Rift Zone. As you can imagine, when the rock rips apart, it allows magma to escape. So we get active volcanoes. We do get some minor earthquakes here, though they're not as significant as the convergent boundaries would be. Often we will see this out in the middle of the ocean. We call that a
ocean-ocean divergence.
mid-ocean ridge, shown here. So the convection currents are actually pulling the plates apart. The magma is coming up in the middle, forming mountains and volcanoes, and again, some earthquakes. Now, there's one tricky thing of this, or actually a couple tricky kind of points here. One is not too bad, and that's the idea that the younger rock is always going to be found right along the ridge, because that's where all this magma is cooling to form new rock. As you get further away from the ridge, the rock age will increase. It gets older and older and older as you get further from the ridge. Now, here's the trickier thing. This rock, when it forms, it actually records the Earth's magnetism. If you recall, we talked about how the Earth is like a giant magnet. But that magnetism changes every so often. And so those changes are recorded.
It depends upon the reversal of Earth's magnetic field. We'll talk about geomagnetism also. Okay, तब आपको समझ आएगा. Because Earth's magnetic field gets reversed once in a while. When the magma is cooling down and solidify, whatever the field is there, accordingly the orientation is given. Okay, earlier it was normal, then became reverse, then again normal, again reverse. This is a continuous pattern which you observe on the oceanic floor. Okay, so that is also considered to be one of the proof behind the seafloor spreading.
In the
Because
rock.
because of
And so
that
what
only we
we
have
see
this
in the
kind of
rock
pattern,
on
right?
either side of a mid-ocean ridge are these alternating bands of magnetism which match up on either side. And that's an important observation because it proves that the rock is actually spreading apart, and it proves that the divergence is actually taking place. So if we look at our reference table, here's the symbol for Atlantic problem. He's plate back with it. And the answer is that these single area of magma that's able to punch through in the middle of a plate. So we're not talking about
ठीक है. एक और चीज़ है ये दिखाता हूँ. इसे बहुत क्लियरली समझ आएगा आपको ये विजुअलाइजेशन से. इट्स वेरी इंपॉर्टेंट. This is how the convection currents move. Rising, converging. You can see the subduction. This is the divergence, ocean-ocean divergence. Ridges, these rift valleys. This is convergence, continent convergence. Can you see subducting plot? How it is generating magma, it is coming up, forming the fold mountains are there, volcanoes are there. This tsunami. Tsunami is the result of earthquake. Okay. So let's stop here. So that is all about the plate tectonics. Okay, so plate tectonics is a very important part. Please revise once from NCRT. So tomorrow we'll talk about volcanism and earthquakes and tsunami also. Okay, it's a small topic. Okay, thank you.